This video tutorial is not intended to replace the information in the Hamilton T1 service manual. Calibration, testing and troubleshooting must be performed according to the instructions in the service manual. This video is intended for certified service engineers only. Here you can see the complete pneumatic schematic diagram for the Hamilton T1. Each line represents a gas flow or tubing connection. By the end of this module, you will have a complete picture of how the whole system works. We will now focus on the O2 mixer components. High pressurized oxygen with a concentration of 100% is supplied to the O2 high pressure inlet port, which flows through the check valve. The check valve ensures that oxygen gas can flow into the device in one direction only. The O2 proportional valve adjusts the flow of oxygen gas according to the desired FiO2 delivered to the patient. Alternatively, oxygen can also be supplied as low-pressure gas through the O2 low-pressure inlet. The oxygen flow is measured by the sensor QO2 before entering the blower module. The O2 mixer assembly that controls the flow of oxygen into the blower assembly consists of the HPO inlet for the DIS or NIST connector. Part of that is the inlet filter that needs to be replaced during annual preventive maintenance. Other components are the HPO check valve, the O2 mixer block, the LPO inlet, the O2 proportional valve, and the O2 flow sensor. In addition, you can see the nebulizer valve attached to the O2 mixer block, which we will talk about later on in this module. Now let's look at the internal flow sensors and oxygen supply specifications. The Hamilton T1 has two internal flow sensors installed. The QO2 is part of the O2 mixer assembly, which is used to control the O2. The Q-vent, which we will see later, is used to control the O2 and ambient air mixture at the blower outlet, and to calibrate the external flow sensor. Both internal flow sensors use miniaturized thermal sensors located on a single CMOS microchip. A controllable heater element is mounted in the middle, and the temperature sensors are mounted symmetrically upstream and downstream in the direction of the flow. Gas flow over the membrane causes a transfer of heat and thus generates a precise measurable signal. A high-pressure oxygen supply, or HPO, must have a pressure of between 2.8 and 6 bars. For the HPO inlet, a connector such as DIS or NIST connector can be used. Low-pressure oxygen, or LPO, must be equal to or less than 15 litres per minute with a maximum of 6 bars. A quick coupling system is used to connect the LPO. The gas source is selected in the application software. Open the Utilities window and then Gas Source. Make sure that there is not an LPO connector connected to the LPO port when you use high-pressure oxygen, as this can result in a technical failure alarm. The use of low-pressure oxygen disables the use of O2 flush and the pneumatic nebulizer, as these functions require high-pressure oxygen. The pneumatic nebulizer is used to provide vaporized medication to the patient. The HPO oxygen source provides oxygen with sufficient pressure to drive the nebulizer jar. The oxygen flow is reduced to approximately 7 to 8 litres per minute by means of an internal flow restrictor in the oxygen mixer block assembly. A valve attached to the oxygen mixer block assembly switches the flow of oxygen to the nebulizer jar through the output connection at the right side cover. If you select low pressure oxygen, this will disable the pneumatic nebulizer. Note that the pneumatic nebulizer is also disabled when the ventilator is used in neonatal mode. The pneumatic nebulizer connects to the pneumatic nebulizer jar adjacent to the external flow sensor. The source gas comes from the O2 mixer assembly routed through the nebulizer solenoid valve and pressure sensor assembly to the nebulizer connection port. Next, we will look at the blower module. The blower module has two gas inputs. Firstly, the medical oxygen gas coming from the O2 mixer. Secondly, the ambient air low pressure inlet. The blower module output is in the direction of the patient. The flow sensor Q-vent is connected to the blower module output. The blower module mixes and compresses the two gas sources. The Hamilton T1 does not need an inspiration valve, as the blower generates the complete breathing pattern. This means the turbine quickly reduces speed during the expiration phase and starts up again quickly during the inspiration phase. The main component of the blower module is the turbine, which is located inside the blower module. The blower module casing dampens the noise from the turbine. The turbine rotates with approximately 60,000 revolutions per minute. A blower cooler is mounted adjacent to the turbine to absorb the heat. O2 coming from the O2 mixer assembly is connected on the inlet tube connector, and ambient air is filtered by a HEPA filter before entering the blower module. Finally, the mixed and compressed gas exits from the blower module outlet port. A pressure sensor P filter is mounted to the blower module, which monitors the pressure drop over the HEPA filter in case the HEPA filter gets clogged. The P ambient pressure sensor is located on the control's electronic board. We will talk about this sensor at the end of this module. Let's take a quick look at the different filters for the Hamilton T1. The air intake to the HEPA filter is mounted in front of the HEPA filter and stops dust from entering the HEPA filter. The HEPA filter will be discussed in detail in the next slide. The air intake filter mounted in front of the fan blocks dust from entering the device. The Hamilton T1 military version has a different HEPA and dust filter to those shown here. The air dust filters must be checked, cleaned or replaced frequently as described in the operator's manual or according to the hospital's protocol. All the filters must be replaced during the annual preventive maintenance. The high-efficiency particulate air filter, or HEPA filter, can filter any particles down to a size of 0.3 micrometers. The Hamilton T1 military version filter and adapter components comprise the following: the military-specific HEPA filter, an O-ring, a filter cover, a NATO standard thread, a dust filter, and an NBC filter canister. Next, we will look at the check valve assembly. The gas coming out of the blower passes through the sensor Q vent and enters the check valve assembly, which consists of the O2 cell, check valve, and obstruction valve. Before moving on to the check valve assembly, let's have a look at how the ventilator controls the oxygen concentration provided to the patient. The amount of oxygen provided is called the fraction of inspired oxygen, or FiO2. The operation of the O2 proportional valve is determined by the following formula. QO2 equals Qvent multiplied by FiO2 minus 21% divided by 79%. As an example, let's take a set FiO2 of 61% oxygen. Given a Qvent flow of 10 litres per minute, we can now calculate the QO2. By substituting the values into the formula, we can calculate that the measured QO2 flow must be 5 litres per minute. And this is finally what the O2 proportional valve is set to. Now we will look at each of the components of the check valve assembly. The outlet of the check valve assembly, also called the patient port, is connected to the patient breathing circuit. The check valve silicone flap ensures that the gas flows in the patient's direction only and not into the device. The O2 cell is mounted directly in the gas path. It also connects the tubes to measure the pressure and to provide pressure to the expiratory valve membrane. We will review this in more detail later. In case of obstructed exhalation, the obstruction valve will open to let the patient exhale through it. The O2 cell performs a monitoring function only. Note that the O2 cell is not required to control the O2 proportional valve and the FiO2 mixture. You might remember having seen that when we made the sample calculation of the QO2. The O2 cell is coded. To guarantee the correct functionality, the device will only accept O2 cells from Hamilton Medical. The warm-up time is less than 30 minutes after replacement of a sensor. The storage temperature range is from -20 through to +50 degrees. The recommended storage temperature range is from +5 to +15 degrees. As the O2 cell is mounted directly in the gas path, it is extremely important that the cell is always installed and tightened to prevent leakage inside the ventilator and possible malfunctioning. The pressure sensor assembly measures various pressure levels. The pressure sensor assembly has internal tubing connections to the check valve assembly and external connections to the flow sensor located close to the patient. The pressure sensor assembly has 5 pressure sensors, 3 auto-zero valves, and the functionality to provide a rinse flow. These functions will be explained next. Let's have a close look at all the components of the pressure sensor assembly. The Hamilton T1 accurately measures flow, volume, and pressure in the patient's airway with Hamilton Medical's flow sensor. This proximal flow sensor lets the ventilator recognize even weak patient breathing efforts. The flow sensor's proximal side, indicated by the blue tube, is connected to the P airway and the left side of the P flow sensor. The flow sensor's distal side, indicated by the transparent tube, is connected to the right side of the P flow sensor pressure port. The flow sensor contains a thin, diamond-shaped membrane within the outer housing that separates the distal and proximal pressure chambers. The membrane allows bidirectional flow through its variable orifice. The area of the orifice changes depending on the flow rate. It opens progressively as the flow increases, creating a pressure drop across the orifice. The pressure difference is measured by a high-precision differential pressure sensor, the P flow sensor, located on the pressure sensor assembly inside the ventilator. The pressure difference varies with flow. The pressure-flow relationship is determined during flow sensor calibration so that the patient's flow can be determined from the pressure drop. The Hamilton T1 calculates volume from the flow measurements. The flow sensor is highly accurate even in the presence of secretions, moisture, and nebulized medications. The Hamilton T1 continuously flushes the sensing tubes with mixed gases to eliminate the possibility of contamination from the patient, condensing humidity in the measuring tubes, and cross-contamination to other patients. This rinse flow is supplied by the rinse flow tank. The rinse flow tank is necessary because the blower does not provide enough pressure to drive the rinse flow during the expiration phase. During every inspiration phase, the rinse flow tank will be filled with air and oxygen coming from the blower. During the expiration phase, the rinse flow valve closes to allow the gas to flow only in the direction of the flow sensor tubing. In this way, the rinse flow tank provides a continuous flow of gas during the expiration phase as well. The pressure sensor assembly consists of the following parts: the pressure sensor board, which comprises the pressure sensors, auto-zero valves, rinse flow valve, and rinse flow tank. Also visible are the tube connections to the check valve and proximal flow sensor for pressure measurement. Let's have a closer look at the pressure sensors and auto-zero valves. The sensor P-vent monitor is the pressure sensor for monitoring and visualization of the values. The sensor P-vent control is for internal controlling and calculation. We will explain the PX valve sensor together with the expiratory valve later on. The functionality of the auto-zero valves is to switch the pressure sensors to ambient air in order to allow for an offset recalculation to compensate for sensor drift caused by temperature change. The auto-zeroing for P-vent sensors, P-vent monitor and P-vent control, is always performed simultaneously, whereby the P airway and P flow sensor sensors are performed at least 30 seconds later. For adult modes, the auto-zeroing is performed at 0, 1, 4, 9, 16, 25, 36, 49 and 64 minutes after starting ventilation, and then every 15 minutes at the beginning of a breath. In neonatal mode, it is performed every 2 minutes at the beginning of the breath. In the event that the temperature inside the ventilator increases or decreases by more than 5 degrees Celsius since the last auto-zeroing, an auto-zero will be performed prematurely. At the beginning of the flow sensor calibration, one P airway and P flow sensor auto-zero sequence is performed. During calibration, the time interval controlled sequences are suppressed. The result of the auto-zeroing is forward to vent alarming only in case of errors. Auto-zeroing of the PX valve sensor is performed during startup and during flow sensor calibration. P ambient is a pressure sensor that measures the absolute pressure. The sensor is located on the Hamilton T1 control board that we cover in the electronics training module. P ambient is used to calculate the flows from the internal flow sensors Q-vent and QO2 from SLPM in ATP, calculate P flow sensor, Compare the P filter with ambient air to check for a clogged HEPA filter. Calculate the monitoring value for FCO2, or the fractional concentration of CO2, and to calculate the monitoring value for FiO2, or the fraction of inspired oxygen. The P ambient sensor also contains a temperature sensor, or T-INSP. The expiratory valve enables gas to escape from the patient breathing circuit in a controlled manner, allowing the patient to exhale. The expiratory valve has 3 pneumatic connections: a tube from the inspiration path, a tube to the PX valve sensor, and a tube to the expiratory valve bleed port. The expiratory proportional valve makes use of the gas pressure to apply the desired pressure to the expiratory valve membrane during the inspiration and expiration phase. Firstly, we will have a look at the ventilator internal expiratory valve assembly and then at the expiratory valve covers. With the help of air pressure coming from the inspiratory path, the expiratory proportional valve applies and maintains the PEEP level during the expiration phase and applies pressure during the inspiration phase to block exhalation. To make this principle work, the air delivered must also have a release. This is realized via the expiratory valve bleed port that leads the air to room air. The P expiratory valve pressure is measured by the PX valve pressure sensor located on the pressure sensor assembly. A microswitch recognizes if an adult or neonatal expiratory valve cover has been inserted. Exhaled gas from the patient enters the expiratory valve cover and gets the desired resistance applied by the membrane before being expelled to room air. The surface of the membrane controlled pneumatically by the expiratory valve is approximately 1.6 times larger than the surface to close the expiratory valve. For example, to apply PEEP of 5, only about 3 millibars of pressure needs to be applied to the membrane. 4 different expiratory valve covers are available, namely an autoclavable and a single use for adult, as well as an autoclavable and single use for infant and neonatal. You should now have a good understanding of the basic pneumatic concept of the Hamilton T1. Please review any part of this module if in doubt, or check with your Hamilton Medical Technical Support representative.